3.3 Combinations in Pascal's triangle. In honor of the French mathematician Blaise Pascal, the array of numbers shown below is called Pascal's triangle. Okay, Pascal's triangle uses combinations in the form row and then the choose function and then term. Okay, so let's take a look at actual Pascal's triangle. So this is what happens. So row 1 is comprised of just a 1, and we actually don't call it row 1. The rows actually start at 0, and the term numbers also start at 0. Okay, so all the way down the sides, we have 1s. And all the way down the other sides, we have 1s. Okay, so row 1 is just 2 1s. Row 2, what we would do is we would add this 1 and filter in that 2. Okay, row 3, we would add 1 and 2, giving us this 3, and then 2 and 1, giving us this 3. Row 4 is the same thing. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And we continuously filter that down. So 1 plus 4, 4 plus 6, 6 plus 4, 4 plus 1. Okay, and so on. And that's how we get each subsequent row, and this goes on forever. Okay, and then what we'll do is we'll name, we'll call, for example, this term is row 6, choose term 0. This term is row 6, choose term 1. This one is row 6, choose term 2, and so on. Okay, all the way until 6, choose 6. And if you put 6, choose 6 into your calculator or any of these row, choose, and then the term number, it will punch you out the input in Pascal's triangle. Okay, so Pascal's triangle is generated by adding the 2 adjacent terms and placing the results immediately below them in the next row. So in regards to term, and so I'm not going to write this as like row choose t, I'm going to write this as more like the choose function and then n comma t, or n comma r, my mistake. Okay, but we're going to quote this in regards to terms. So let's take a look at this. Term, and then we have row n, term r, and then term, row n. So same row, but the next term, because instead of r, it's r plus 1, which is the next term beside it. What that's going to equal is it's going to filter down to the next row, so row n plus 1, and it's going to shift to the right. So whatever this one is, r plus 1, that one's going to be r plus 1 again. Okay, so the term in row n of Pascal's triangle, we can either write it with t's or with c's. So NCR plus NCR plus 1, right, the next term, is going to be the next row, the next term. Okay, and I already went over this. All row and term numbers begin with that 0. So let's take a look at the patterns in Pascal's triangle. Okay, first of all, the first diagonals, all 1s. Okay, we already saw that. The second diagonal increases by 1 each time. If you actually take a look here, these are actually the row numbers. That's second diagonal. And that second diagonal, there's symmetry there. Okay, so I actually touched on symmetry, second diagonal. Now, third diagonal. Okay, what happens is 2 consecutive numbers add to perfect squares. So 1 plus 3 is 4, and you can root 4. It's 2. 6 plus 3 is 9, and you can root 9. 6 plus 10 is 16, and you can root 16. 10 plus 15 is 25, and you can root that. So they are perfect squares. Okay, now hockey stick pattern. For the hockey stick pattern, if you start at the 1 and you go down and you make a hockey stick, and it doesn't matter where you finish it, it could be like 1, 2, 3, 4 terms, or 1, 2 terms. Okay, the rule is that this diagonal here, so 1 plus 3 plus 6 plus 10, actually equals the number in the blade. Okay, so 1 plus 5 equals that 6. Okay, 1, 2, 3, 4, 5 will equal the 15, and so on. Okay, and then there's one more pattern that we're going to touch on, and that's when we add all the numbers in any of these rows, so row 6 or row 5, and we take the sum because we add them, what's going to happen is the sum of the row n equals 2 to the n. So it doubles every time. So this one is 2, this one is 4, or sorry, this one is 1, this one is 2, this one is 4, this one is 8, it's going to be 16, 32, 64, and so on. It's going to double each time. Okay, so example 1, the first 6 terms in the row 25 in Pascal's triangle are, and then I have them written below. Determine the first 5 terms in row 24 and the first 6 terms in row 26. Okay, let's figure this out. So row 26 is actually the easier question. This branches to a 1. Then let's add. 1 plus 25 is 26. 300 plus 25 is 325. 300 and 2300s is 2600. 2300 and 12,650 is 14,950. 12,650 plus 53,130 is 65,780. Those are the first terms in, like the first 6 terms in row 26. Now, if we're working backward, the 1 also goes up. Now, 1 plus what number equals 25? Well, that's 24. And we can also see the pattern in the second diagonal, 24, 25, 26. Okay? So then 24 plus what number equals 300? Essentially, we're just doing 300 minus 24. So we get 276. Oops. Okay, 276 plus what number equals 2300? So I'm going to go 2300 minus the 276. I get 2024. Okay, what number minus 2024 is going to give us 12,650? Just subtract them. I get 10,626. And I obviously double check. And then what number, 1, 2, 3, 4, 5, plus 10,626 is going to give us 53,130. I get 42,504 up there. Okay, and then those are the first 6 terms in row 24. Okay, let's use Pascal's triangle to write a formula for each of the following terms. Okay, so the term in row 37 and then term 12 and the term in row 37, term 13, what's going to happen is these two, because they're in the same row, they're going to add to the next row. So if we think about the next row, it wouldn't be 37, it would be now 38. And then we always take this number, the n plus 1. So 38, 13. I said n plus 1, r plus 1. Okay, term 50, 44, and then 50, 45. So the next row is 51, and the next term, that's going to match. That's the 45. Okay, so if we have term in row 12, and then we have term 5, we kind of want to think backwards. Where did this come from? So we know that this came from row 11. Okay, and this 5 has to match here, so that's going to be 5 and 4. Okay, and then term 4032, where did this come from? Well, these came from the 39th row, and it came from 31 and 32. Right? These have to match. Now, the sum of a horizontal line in Pascal's triangle equals 2 to the n. So what is the sum of the following rows in Pascal's triangle? So the sum of row 6 is going to be 2 to the exponent 6. And if you put this in your calculator, we get 64. The sum of row 22 is going to be 2 to the 22. And if we put this in our calculator, we get a really big number. 4,194,304 would be the sum of that row. And then simply in general, the sum of row n is just going to be 2 to the n. So again, that's a general formula. You can just sub in any row number for the n. Okay. Now, if we did this backwards and we said which row in Pascal's triangle has the sum of its terms equal to the following. So we're going to say sum of row n equals, well, this is going to be 2 to the n. It's also going to equal 1024. And if you want it math-wise, we can sub the 1024 equals the sum, 2 to the n. So we can go ahead and do a trial and error, okay? We know from above it's going to be bigger than 6, is going to be smaller than 22. So let's try 2 to the 10, okay? So here's my work on the side of my paper. 2 to the 10, oh, that actually worked. 2 to the 10 equals 1024. Therefore, since everything aligns, we can say n equals 10. Okay, so the 10th row has a sum of 1024. Now let's do the same thing. Let's do this for 256. Okay, we know it's going to be bigger than 6. I'm going to actually try 7 because it shouldn't be that much bigger than 6. Okay, 2 to the 7 is 128. Let's try 2 to the 8. Yeah, that's our 256. So 256, in other words, is 2 to the 8. Okay, I'm going to highlight that. N, that's what we're solving for. Everything else is identical. N equals 8. The 8th row has a sum of 256. Okay, the exact same thing for 32,768. Let's do this 2 to the n. So 32,768 equals 2 to the what? So we know it's going to be bigger than 10 because 10 was the 1024. So let's do 11. 2 to the 11 is 2048. 2 to the 12, 2 to the 13, 14, 15. Okay, and I just did these in my computer or my calculator. 2 to the 15, 32,768. 32,768 equals 2 to the 13. If you think about these numbers equaling each other, we can simply put n equals 13. The 13th row has a sum of 32,768.